In this video, we will be solving this question which says a square matrix of zeros and 1 in which the sum of the elements in each row and each column is exactly equal to 1 is called a permutation matrix. And we have to show that any 2 cross 2 permutation matrix P is invertible and we have to find its inverse. So consider you have this matrix which is of 2 cross 2 dimensions and the elements are A, B, C, D. For this matrix to be permutation matrix, we want that the sum of the elements in each row and each column should be exactly equal to 1, which means your A plus B should be equal to 1, your C plus D should be equal to 1, A plus C should be equal to 1 and B plus D should be equal to 1. And we are also given that A, B, C, D either take value 0 or 1. Consider first case. If your A is 1, then this equation will yield that B is equal to 0. This equation gives that C is equal to 0. And if C is 0, then your D is equal to 1. So when A is equal to 1, your matrix becomes 1, 1, 0, 0, which is a identity matrix. Consider the second case. If your A is 0, then A plus B would be equal to 1. This means your B is 1. A plus C is equal to 1. This means your C is 1. B plus D is equal to 1, which means your D is 0. And in this case, you will have a matrix 0, 1, 1, 0. Since the values of A can take either 0 or 1, therefore there are only two possible cases. So let's consider case 1. When your A is an identity matrix, in this case the determinant of A is equal to 1, which is not equal to 0. This means your matrix is invertible. And to find the inverse, we will be using this formula where A inverse is equal to adjoint of A divided by determinant of A. The determinant of A is 1 and adjoint would be this. So your A inverse is nothing but 1, 0, 0, 1. This gives us that A inverse is equal to A. Let's consider case 2. When A is equal to 0, 1, 1, 0, here your determinant is equal to minus 1, which is again not equal to 0. Thus your matrix is invertible. Now let's find the inverse of this matrix, that is A inverse. Again we will be using this formula, that is A inverse is equal to adjoint of A divided by determinant of A. This means that A inverse is 1 divided by minus 1 multiplied by this matrix, and by doing the calculations you will get that A inverse is equal to 0, 1, 1, 0, which is again equal to A. Thus we have shown that the matrices are invertible and we have also found their inverse. Now moving on to the second part, we have to show that any positive odd integral power of a skew symmetric matrix is also skew symmetric. Now let A be any skew symmetric matrix, then A transpose is equal to minus A. And now we have to prove that A to the power n transpose is equal to minus A to the power n, where n is an odd integer. So let's begin with the LHS, that is A to the power n transpose. This can be written like A dot A dot A dot till A n times, and we have to take the transpose of A. Now using the property that AB whole transpose is equal to B transpose multiplied by A transpose. So we can write A to the power n transpose as A transpose multiplied by A transpose, and this goes on for n times. Now we are also given that A is a skew symmetric matrix. This means that A transpose is equal to minus A. Thus this equation becomes minus A multiplied by minus A for n times, and remember that n is odd. So A to the power n transpose is equal to minus 1 to the power n, as I have taken minus 1 common, and this is A to the power n. Now when n is odd integer, that means minus 1 to the power n is nothing but minus 1. Thus your A to the power n transpose is equal to minus 1 multiplied by A to the power n, or A to the power n transpose is equal to minus A to the power n. which was something we were asked to prove.